Welcome to my talk. My name is Felix Ruess. I'm from Roboception. And I'm here to briefly talk about the driver that we wrote for our 3D stereo camera sensor. So let me briefly introduce Roboception. We're a pretty young company, 3.5 years old, based in Munich, founded by 3 former DLR employees. And we're currently 18-ish people. So our slogan is Sense, Reason, Act, and our mission is to go from pixel to action using perception. So we're mainly focusing on the perception part right now, but we want to make it easy to use standard perception packages to then actually do the action. So if that works. Yes. Just to briefly maybe elaborate our business model, or actually like the stuff that we sell. So as the base, basically we have our sensor, so a 3D stereo sensor called the RC Wizard. That's like a smart camera, so we can run additional software modules on the camera itself. There are a couple of them that I will briefly introduce later. And then we have the RC Reason software suite, so we call it, that can run on top with additional modules that can either run, in some cases, on the sensor, or you deploy them off-board, but use the capabilities of the sensor. So this is an example, or 2 renderings of our sensor. They basically come in 4 simple variants, of course, monochrome and color. And we have 2 different baselines, so a 65mm baseline for when you want to get closer to objects, and a 160mm baseline for when you don't need to get as close to maybe like grasp it directly. So what's actually running on this sensor itself? So we have a GPU, an NVIDIA Tegra on board, and we have quite a little bit of computing power to do additional processing. And what we can see, so we have our standard 2 cameras. We rectify the images, put that into semi-global matching to get a dense disparity image, so basically what we can then get a point cloud from. But also additionally, we run visual odometry on the sensor. We have an IMU on board that is then fused with the visual odometry and can provide 60 pose estimates in real time with 200 hertz. Additionally, optionally, we have this SLAM module that can basically close the loop. So when you have visual odometry and IMU only, it will eventually, of course, drift over time. So we can run also SLAM on board to compensate this drift. So this is an early example of how the output of our sensor looks like. So here on the bottom, on the top right, you can see a colorized disparity image. And what's nice is that basically for every pixel that we can calculate a disparity for, we also calculate an error. And then we also have a confidence value that tells us how sure we are that this error is actually correct. And this is basically, we take advantage of this error and the confidence in all our later processing pipelines to wean out points where we had like reflections or we're not as sure that it's actually correct. And as I mentioned before, so we also have visual odometry fused with the IMU running on board. So what you see now here is basically we just use the real-time estimate that we get from the sensor, and this is actually just taken from RViz. So we basically just set decay time for the point cloud and move the sensor around, and we can see that there's very little drift, and we can basically this way get a very simple 3D model without doing any ICP registration or anything after that. So we have some additional modules that can run on top. For example, SLAM that I previously mentioned already. Then we have a very simple like tag detection where you can detect April tags and QR codes. And we have item pick, which I'll also quickly show. But first to SLAM. I think SLAM is, everyone knows what that's supposed to mean. So basically, we run an optimization over everything. But already, if we don't use SLAM, so this is an example here of us running in a loop, like down our staircase, outside in the courtyard, once around, and we already have not that much drift over this time. So here you can also see again the depth image, the corresponding confidence image, what the left camera sees, and here, for example, then just a point cloud projected in Arvis. So what this shows is that you can basically already, with what comes with the sensor out of the box, navigate around your environment and get a, in most cases, pretty good localization. And of course, the next step is then if you use this onboard SLAM module, where you can also close loop errors and so on, and build an off-board 3D map. So we don't have enough processing power, or actually rather memory and storage capability on the sensor to store like a full 3D model of the world on the sensor, but we give you all that you need to do that off-board. So basically you get with 200 Hertz, you get all the poses, and you can get the optimized trajectory of everything later on, and here basically we just put this in an octomap that is also enhanced using these aerometrics that we got to use that in the probabilistic update of the octomap. Okay, yeah, there's another module that can run on board that we made a ROS interface for. It's called item pick, which is basically meant to solve like the 80% problem when you want to pick something from a bin with a suction cup or a suction gripper. All it does, it basically looks for a bin. You can specify the dimensions, and then you specify like how big is my gripper and what's the maximum curvature my suction cup can deal with, and it will look for graspable surfaces within that bin and directly give you the grasps that you can go to with the robot. And to make this easy to set up and configure and also like supervise, we have a web GUI that's basically a web interface that's running on board the sensor. So you can just discover the sensor, double click, and you will end up on the web server, and you can then like see the live camera image, configure everything, and get running very quickly. Okay, so how does this look in some more practical example? I thought I'll pick hand-eye calibration here as an example, as that's often needed with robotic manipulators. So here usually you have two distinct cases, right? Either you mount some sensor on the robot itself, or you mount it statically, but in each case you have to do hand-eye calibration in order to relate the two coordinate systems to each other. So in our case we made a very simple setup. So basically you just set the size of the calibration grid, then you tell the sensor what is the current robot pose. It will internally store these pictures, and when you have enough pictures taken, it will evaluate if they're different enough so that it can actually calculate a hand-eye calibration, and then basically just stores the hand-eye calibration on the sensor. And this routine makes it very easy to integrate with, for example, directly the robot controller that doesn't have capabilities to receive images, run calibration routines. So here you just have REST API calls directly from the robot controller to do this hand-eye calibration. Okay, so how does this actually all fit into ROS? But before I talk about that, let me briefly backtrack, since while we use ROS on the sensor, at least for the non-real-time parts, we don't have the ROS master exposed to the outside. So what we have as interfaces is mostly a REST API that basically bridges all the dynamic reconfigure parameters, so stuff that you can change, service calls, and so on. So it's a rather simple mapping, I would say. And then, like, to configure the camera-related parameters and actually stream the images and so on, we use a standard proven interface for industrial cameras, namely like GigaVision, and then on top of that there's a GennyCam which can generically describe any camera. So you can directly use our sensor with any software that already understands GennyCam or GigaVision, which is of benefit for most of our industrial customers that don't use ROS. And then also we have a very simple interface for real-time poses, which we basically just stream UDP packets with protobuf encoded poses. Okay, so now how did we actually go from this to something with the usual ROS feel. So first of all, we made a convenient library to use these GennyCam GigaVision cameras. Actually, you could also plug in a different transport layer here and use USB 3 vision or something like this. So this is completely vendor agnostic, and it's actually also ROS agnostic. And then the same basically we made for our simple Dynamics API. So we made basically these two generic ROS independent libraries that we then used for the RC Wizard driver, which is then our ROS driver, which calls into those libraries here to actually do the communication. So in the end, hopefully what you have is what you expect from any good ROS driver, right? It's boring, it just works. It just has topics you subscribe to, you have dynamic reconfigure to change everything at runtime, and hopefully if it's boring enough, it means it works well. On top of that, of course, we have like the usual things that you want to have. We have like a small model for RViz and Gazebo, so you can use it in simulation and in visualization. We have an integration with the onboard SLAM module. And of course, we spent quite a bit of time on documentation and tutorials on how to get started using ROS with our sensor and integrate it into standard ROS packages. So this is basically one video that we made for the end of this FTP. Here we show, it's a bit laggy here, it's working fine here. All the drivers that we made integrated into the standard ROS navigation stack. So we didn't need to change anything in the standard ROS navigation stack, but what we do here is basically we have this Turtlebot where we mounted our sensor, and we drove around the office once, recorded a map, then using it offboard in Octomap. And we had these tags that are also detected on the sensor itself, that are then augmented in the map, and we use the localization that is provided by the onboard SLAM package. And then in the end, we just plug this into the normal ROS navigation stack, into MoveBase basically. And then we have our mobile Apple delivery. So we go to our food picking station, where our other robot uses our onboard item pick module to detect tags that you previously quickly saw here. And it will just, as soon as it sees a tag, it will deposit an apple. And then you can just click an RViz to deliver an apple to your office. So this is basically a demo that we came up with that integrates all the different things that we did. And then it will go to the office with the respective tag, check again, oh yeah, is that really Corby's office? Yes, that's Corby's office, so Corby definitely needs some vitamin C. And yes, he gets his vitamin C delivered. And then basically after that, the robot will just wait for the next order or drive back to the automated Apple pick station to get refilled. And I was also quite happy that, so based on this tutorial example that we made, maybe I'll just let it play to the end. So based on this example that we made, we were very happy that Pile Robotics, I think just yesterday, released a video where they basically did pretty much exactly the same, just with their robot, and also just stuck the RC Wizard on top, used it for the navigation part, and now what they do here is not deliver apples, but rather, since programmers need caffeine, I guess they deliver some caffeine soda cans. And yeah, as you can see here, also it's usable indoor and outdoors. And this is an example of how the web GUI looks like if you wanted to just directly get an idea of how things look there. And yeah, here also they map the environment, pre-map the environment. Of course, you're totally free to use all the available ROS packages for exploration instead of driving it around before yourself. But then basically you're back into normal ROS land, and you can take advantage of what's already there in terms of 3D perception and SLAM. You don't have to worry about that part, but you can worry about implementing your exploration algorithm or something like this. Yeah, with that, I'm finished. Thank you for your attention, and I'm open for questions.